Okay, so hello, I hope I am audible, right? And my screen is also visible. And today is actually this is going to be tutorial number 9, but this tutorial was supposed to happen yesterday, Saturday, from 6 p.m. to 8 p.m. But there was a technical issue from my side, so that's why I am not able to record the tutorial session. So that's why I called up the tutorial session, and instead of yesterday's, I have asked the NPTEL team to schedule it today, and right now it started. So this is tutorial number 8, 9, 9. Today is 22nd March. So today we will be discussing many things. So starting with the till last class, we have discussed primary decomposition theorem. So what primary decomposition theorem says that let primary decomposition theorem. What this primary decomposition theorem says that let P from V to V be a linear operator on a finite dimensional vector space V, on a finite dimensional vector space V over the field F. Let P be the minimal polynomial of T, and P is actually has a specific decomposition, that is P1 to the power R1, P2 to the power R2, all the way Pk to the power Rk, where these Pi's are distinct, irreducible monic polynomial, and this R1 all the way Rk are positive integer. That means natural number. Okay. Then what this says, let kernel, one second, let kernel of Pi to the power R1 T is equals to Wi for all I equals to 1 to K. Then first fact is that these Wi's are invariant under T. Second fact is that the vector space V is actually direct sum of W1 direct sum W2 plus Wk. That says that this W are not only invariant, this Wi intersection W1 all the way Wi minus 1 plus Wi plus 1 all the way, this is Wk, these are the disjoint. Okay, that is for all I. Okay, and third is that here we have said that Wi's are invariant under T. So if we restrict T to Wi, then if I write it like the minimal polynomial, basically the minimal polynomial for T restricted to Wi is Pi to the power Ri. This is what it is, primary decomposition theorem. So according to the primary decomposition theorem, we can actually main target in this linear algebra before till the inner product space, that is that if you have a matrix, then your task is to express that matrix in a simpler form. I mean, whatever the simpler is possible. The most simplest form is the diagonal form. Simpler up to equivalent. That means up to equivalent, you have to express that matrix to a simpler form. Up to equivalence means we want a simpler form of the matrix which is equivalent to the given matrix. And the most simplest form of a matrix up to equivalence is the diagonal. But always we may not have that privilege to have the diagonal possible. So in that case, we want a simplest form of the matrix T or the linear operator T. So in that case, whenever you have the invariant subspace Wi, so then the matrix representation T with respect to order basis, suppose let then if Bi is the order basis of Wi, then clearly then B1 union B2 union all the way union Bk is an order basis of V, right? So now, but interesting fact is that this T restricted on Wi, they are invariant. Okay, so that means if I apply linear operator T on the vectors coming from Bi, then that will going to be a element in Wi. So that means the matrix representation with respect to this basis with respect to this basis is T restricted to basically matrix representation T with respect to W1 with respect to the matrix representation of T restricted to W1 with respect to the basis W beta 1. Next is the matrix representation of T restricted to W2, its matrix representation with respect to beta 2, and in this way this will be a diagonal form. So this is the whole matrix. So this is somehow simplest form. All other entries will be 0. So therefore, this is the simplest form right now, whatever simplest form. But if I want to go more simplest form, that is, let's break this matrix or let's convert this matrix to its simplest form. So target is now reduced to find a simplest form of T restricted to Wi up to equivalence, up to similarity. This is the target. So if I can, suppose you choose, yes. Restricted linear transformation is that, suppose here we have linear transformation V to V, right? Let's take W is a subspace of V. Then we know W is invariant if TW is subset of W, right? So therefore, we can consider invariant. If we can consider T as an operator, which we denote by T restricted to W, that is operator from W to W. Symbolically different, but it is actually, I mean, T restricted to W means T is the bigger operator that acts on every element of V. But T restricted to W means this is the operator which will be act only on W. Okay, and automatically basically if I take a vector alpha from W, then T restricted to W, this is I am calling it as operator. This at the point alpha is nothing but T alpha. This is not separate. This is same thing, but okay. So this is what it is restricted. So that's why the matrix representation will be like block form. There is no doubt about this, because if you even, for example, if you take suppose alpha 1, alpha 2, alpha k, and another basis is like beta 1, beta 2, beta k, and let's take this is W1 spanning this set is spanning W1 and this set is spanning W2. Now as I have said, W1 is invariant under T, W2 is invariant under T. If I apply T alpha 1, T at the point alpha 1, that will be some element in W1. That means that will be some scalar multiple of alpha 1, alpha I. Similarly, T alpha 2 also will be Ci2 alpha I this way. T alpha k will be summation of Ci alpha k. So matrix representation will be corresponding to this. Matrix representation will be like C11, C21, like this way, and up to Cik. And below term will be 0. Below term corresponding to beta 1, beta 2, beta k. This is how it is. The total basis is alpha 1, alpha 2, alpha k, and beta 1, beta 2, beta k prime, something like that. So that's why matrix representation look like this way. This will be 0, this will be 0. There will be some possibly non-zero term, and there is possibly non-zero term. Is this clear? So if it is clear, then I think this expression will also be clear. So up to similarity, I want, so basically we are getting some simplest form, but we want more simplest form. That is, suppose we have a t restricted to wi, okay, and then we want the simplest form of that matrix. But recall that t restricted to wi in primary decomposition, basically I am trying to study the rational canonical form. So that will start from the primary decomposition theorem. But okay, so basically, if I want to find the simplest form of the main matrix, bigger matrix, then it is enough to find the simplest form of this matrix. But for this matrix, for this operator or matrix, the minimal polynomial is minimal pi to the power ri, right? And pi is an irreducible monic polynomial. So therefore, our task will be to find the simplest form of a matrix whose characteristics, whose minimal polynomial is something like this. That is the power of power of a irreducible monic polynomial. Okay, so in that case, we have a cyclic decomposition theorem. Okay, so cyclic decomposition. What cyclic decomposition theorem says? Cyclic decomposition theorem says, I mean, these are the path through which one will get the Jordan canonical form. First primary decomposition theorem, then cyclic decomposition theorem, and then you will be reached to Jordan canonical form. Okay, so cyclic decomposition theorem says, okay, before that, cyclic subspace. I want to give a cyclic subspace, and there is many things I should say, but I will try to do it quickly, unless if you have any specific, doubt in that things, then you can ask me, because there is lots of things I am trying to quickly cover how to get the rational form of a matrix. Let t from v to v be a linear operator, alpha not equals to 0 be an element in v, then this is the notation z alpha t, that is the t cyclic subspace gt alpha, such that g is any polynomial. This is the field of polynomials over f. That means you can consider f is complex or real. That means the real polynomials are complex polynomial. This is what it is, and this is called t cyclic subspace generated by alpha. T cyclic subspace of alpha. Okay. Now, corresponding to these two, we will be consider the ideal I alpha, that is equals to all those polynomial g coming from f of x, such that g of t alpha is equals to 0. This is called annihilating. I think this is called annihilating T annihilator. So what T annihilator does, actually, T annihilator does that. So basically, what is the connection? These two things, there is a connection. What is this connection? So first thing is that, suppose you have alpha, okay, so vector alpha, and you are considering all the this is basically, one can say that t to the linear span of t to the power k alpha. K is some natural number. This is what it is. Span closure of this. Okay. Now, here ideal is that all those g such that gt alpha is equals to 0. Okay. So basically, as characteristics polynomial and minimal polynomial makes, if I consider the minimal polynomial mt, that we know that will be 0. If I take characteristics polynomial ft, that will be 0. So that means this characteristics polynomial, minimal polynomial, all will be there. But this will form a ideal. Okay. But we are considering the ideal, which is consisting all those polynomial g such that gt at the point alpha is equals to 0. So there exists unique monic, not irreducible, monic generator of I alpha, which is called the T annihilator. This is called T annihilator, called T annihilator, called T annihilator of alpha, denoted by, that is a polynomial P alpha, that is the smallest polynomial. Any polynomial which will annihilate this, that will be the multiple of this polynomial P alpha. So what is that connection? Connection is that if degree of P alpha is n, then, or r, then this Z alpha T, that is the T cyclic subspace, is an R dimensional subspace, and Z alpha T will be automatically invariant subspace, and Z alpha T is actually span of T to the power, span of alpha, T alpha, T square alpha, all the way T r minus 1 alpha. Basically, let's take this is K, T to the K minus 1 alpha. So why I am going to like this way? That is something going very different direction. It will seem to like that, but the fact is that one can do the cyclic purpose of the cyclic decomposition is okay. So note that this space is actually this space is invariant under the operator T. This is what it is. This is a smallest subspace. This is a subspace which is invariant under T. For a vector alpha, we can choose. We can choose a non-zero vector in V, and we will get a smallest subspace alpha, T square alpha, T to the power K minus 1 alpha. So and such that space will be invariant under T. Okay. So in fact, problem is that if we take T to the power K alpha, here we have up to T K minus 1, T to the power K alpha, that will be linear combination of this C1 alpha 1 plus C2 T alpha plus C3 T square alpha, all the like we can write T to the power K alpha as a linear combination of this. So that means if you look at carefully, here we have obtained T restriction of W1. This is something, W1 is there. W1 is suppose W1 is the invariant subspace under T. Now we choose an vector alpha coming from W1, and we consider the subspace which is smallest subspace containing alpha, that is like alpha, T square alpha, T to the power K minus 1 alpha, such that is invariant. So then that will be invariant under T. So then we will be, suppose we have T restriction of W, we will be breaking this W1 once again in subspaces, something like this. Here will be term, here will be term, here will be term, and this is 0. This is the target. Okay. So here comes the cyclic decomposition theorem, and cyclic decomposition theorem is that, okay, before that, as I have said, this is invariant under T, and matrix representation of T restricted to Z alpha T as an operator, Z alpha T, that is companion matrix of P alpha. So basically what I am saying, suppose we have a P alpha is as I have said, P alpha is of degree of P alpha is K. So let's take P alpha X is equals to C naught plus C1X plus all the way C, this is monic polynomial, P alpha is a monic polynomial, so this will be like Ck minus 1 x to the power K minus 1 plus x to the power K. Then companion matrix for this matrix of P alpha, that is equals to 0 1 0 0 0 0 0 1 0 0 0. So all the way second last column will be like this way, and the last column will be like minus C naught minus C1. I hope I'm writing correctly. Yeah, all the way minus CK minus 1. This is the component matrix. In fact, if you take, this is the basis vector, order basis, this alpha t square alpha t to the power k alpha, and suppose this is invariant subspace, and we have this p to the this one, then the matrix representation of t with corresponding restricted to this will be this one with respect to this basis. That is very much clear, because t will send, suppose let's take the basis beta 1 is equals to alpha, beta 2 is equals to t alpha, beta 3 is equals to t square alpha, all the way it will go, and beta k is equals to t to the power k minus 1 alpha. Then t beta 1 actually t alpha, which is actually equals to beta 2, t beta 2 which is actually t of t alpha, which is actually beta 3, and all the way t beta k which is actually equals to t of t to the power k minus 1 alpha, which will be t to the power k alpha. But p alpha t alpha is equals to 0. That says here is the t to the power k alpha. T to the power k alpha is equals to minus c naught identity minus c1 t alpha minus c naught alpha, and all the way minus c k minus 1 alpha to the power k minus 1. So that is what alpha to the power alpha t to the power k minus 1 alpha. So if we express this, this is the last column we will get. So this is the component matrix, and this is the smallest form of a matrix one will get. And no, and before, after that, no simpler form is possible. So why one? What is the advantage? So clearly, it is advantage that if you have a companion, if you have a base, if you have a set like this, which is invariant under T, you can get the matrix representation like this. And that is component matrix of some corresponding to some polynomial. Now the cyclic decomposition, how the cyclic decomposition helps here to simplify things. Cyclic decomposition theorem says that okay, cyclic decomposition theorem, what this says, let T from V to V be a linear operator on a finite dimensional vector space V whose minimal polynomial is P1, P to the power n, where P is monic, like T restricted to Wi, monic, irreducible, polynomial over the field F. Then V is direct sum of cyclic subspace, T cyclic subspace in this way: Z alpha 1, T, direct sum Z alpha 2, T, direct sum Z alpha, T, alpha k, T. I think this is already scale. Okay. So these are the cyclic subspace corresponding to the vector alpha and alpha to alpha k, and they are something like, you have their alpha and alpha to alpha k, they are distinct vector, no doubt. And if the corresponding annihilator and corresponding T annihilator, because as we have seen in the beginning of today's this tutorial, that if we have a T cyclic subspace, you have a companion. So if you have a T cyclic subspace, you have a T annihilator. Then corresponding T annihilator of Z alpha I, T is P alpha I. Then or Pi, let's take this as Pi, and so the corresponding annihilators are, this will be the interesting fact, these annihilators are this P to the power some Ni with P to the power N with, okay, Pn1 all the way Pnk. These are the annihilator, same polynomial P here, okay, with a different power I'm right now writing, but with the fact that this N1 will be exactly N and all other will be like less than equals to all the way less than equals to Nk, but importantly their product will be N exactly N, that N1 N2 all the way Nk will be exactly N. This is what it is, the cyclic decomposition theorem. So what cyclic decomposition theorem says something, I mean there is many things, but main point is that you will get a very simpler form with this decomposition. Suppose you have vector alpha 1, alpha 2, alpha k, such that you can write v into this form. Okay, I mean recall that we have t cost t restricted to wi. For this the minimal polynomial is p I to the power ri. So let us take this wi as v here in this purpose, in this settings. Let's take this wi as v. Then t is right now a linear operator from v to v, and for which the minimal polynomial is this. Then we will have a decomposition of the vector space v such that the corresponding this subspace, t cyclic subspace corresponding to this t cyclic subspace, the annihilators are p and p to the power n and p to the power nk. And starting with, sorry, here I have written little low. This is not correct. This will be the actually, this is something different. This will be corresponding to the algebraic multiplicity, but that I'm not going to discuss. So, but the point is that you can decompose like this way, and corresponding to the annihilator of t is look like this way. The annihilator look like this way. Now, whenever you have annihilator look like this way, and as I am saying, these spaces, this z alpha 1 t, z alpha 2 t, these are invariant under t. So that means t restricted to this z alpha it, they are actually some block form. So the matrix of t with respect to v, then t matrix representation it will look like t restricted to z alpha 1 comma t restricted to z alpha 2 comma t, like this. So you can go like this way, and t restricted to z alpha k comma t. But each of them matrix representation are actually companion matrix of this p to the power n1. Okay. So these are the companion matrix for the p to the power n1. Okay. So that means there will be companion matrix. This will be, so that is basically like companion matrix of p to the power n1. Next one will be like companion matrix of p to the power n2, and like this we will go. So these are the something more simplest form. So recall that we have initially started with the primary decomposition theorem. So you have a linear operator t from v to v. First we have decomposes v to direct sum of wi, where each wi are invariant under t, and restriction of ti. For this the minimal polynomial is pi to the power ri. Now corresponding to these spaces, we have this type of decomposition. Corresponding to this particular block, we'll have this decomposition, and this is the simplest form. And this is called the rational canonical form of T. This is what it's called, the rational canonical form of T, or of some matrix. So now let's come to the first questions of today's tutorial. And these questions is there, so that's why I'm going to discuss this lots of theorems. So this is the first question. So what this first question says, if T is a linear operator on a vector space V of dimension 6 is the dimension over R, real number, having the minimal polynomial as t square minus 3t minus 4. So minimal polynomial for this is actually, here it is x, okay, x I can write, that doesn't matter, x square minus 3x plus 4, and another factor is that x square minus x plus 2. Note that over R they can't be factor more, but if we consider it is over complex, then we can factor it, right? This is a quadratic equation. In complex field there is a root, but in real field always you will not have this factorization. Here is also similarly, you can factor it in the complex field, but not in actually in real field we can't factor it. So now if we consider this is like P1, this is the P1, then R1 and P2 to the power R2. Here R1 is actually 1 and R2 is equals to 1, and P1 is equals to x square minus 3x plus 4, and P2 is equals to x square minus x plus 2. So now we will have a decomposition of the vector space V to some subspace W1 direct sum W2, where the t restricts, I mean here wi is actually equals to, basically wi is actually p1 t kernel of p1 t, and w2 is equals to kernel of p2 t, and we have a decomposition. So matrix will be, so matrix of t will be t restricted to w1 and t restricted to w2, right? This one is there. Okay. Now if I take each of the space wi, now t restricted to w, we have these are the polynomials, right? And we can't decompose it. Now let's go to the cyclic decomposition theorem. Okay. Now if I go to the cyclic decomposition theorem, that if I go to the cyclic decomposition theorem, that we will be able to decompose these spaces into further spaces, and with the what is called the, with the minimal polynomial is p2, minimal polynomial will be starting with p1 and all other will be similar to p1. Here is no other factorization is possible. Here n1 is 1, so here n1 is 1, so n2 will be 1, and if there is more factor, then n2 will be 1, n3 will be 1, and all the will be nk, right? So now corresponding to this polynomial x square minus 3x plus 4, the component matrix is so this is 3 by 3 will be, because that is in degree k, then that will be k by k. So here we have, so 2 by 2, 0 1 and minus c naught, so it will be 3, and this is the last entry. I think this is correct. Oh no, sorry. So we have to consider it c naught plus c1 x plus x square. We have to consider it like this way. So then it will be like 0 1 minus c naught minus c1. So c1 is at 0 1 and c naught is actually 4, and c1 is actually minus 3. So minus plus. So this is one of the component matrix block will be there. Okay, and corresponding to this t restricted to wi, if I do the cyclic decomposition, so what we'll have? We'll have one factor p1 to the power r1 is 1. Another factors will be like, what are the possible factors? P1 to the power r2, where r2 has to be less than equals to 1, that is means r2 can be 1, or either it is 0 or 1. Okay, there is no other choice. So that means we may have this factor repeatedly, or at least once. At least one will be there, but we may have repetition. Okay. Now corresponding to the other, so now let's go to the t restricted to w2. So now consider t restricted to w2. So then minimal polynomial is x square minus x plus 2. So corresponding component matrix is, this will be like 0 1, and it will be like 2 1. This is what it is, the component matrix. Similarly here p1 p2 power is 1. So if I have the cyclic decomposition and we have more alpha 1 alpha 2 alpha 3 something like that, all other will be like p2 to the power 1, and all other will be same component matrix will be there. So similarly here we may also have the repetition of this factor, or either at least one times, at least once it will appear, or repetition of this factor. So that means, but here the vector space V is actually of dimension 6. Okay, so now how at least once they will appear? This is the first thing, at least one they will appear. Another thing is that they can repeat, but if it repeats, either it will only repeat, or it will only repeat. Both can't repeat, or none of them can't repeat more than twice. So that means the corresponding rational canonical form is zero 4 1 3. This can repeat at least, they should appear at least once. First fact is there. These are the diagonal blocks. These are the blocks actually. These are the blocks in 6 by 6 matrix. Or suppose it is repeating 0 2 1 1, 0 2 1 1, diagonal blocks. This is also diagonal blocks. Diagonal blocks in 6 by 6 matrix. So these are the options. So 0 minus C naught. Okay, sorry, it will be minus C naught, minus 4. Then it will be minus 2. Minus C1, yeah. Minus 4, minus 4, minus 2, minus 2, minus 4. So 0, minus 4, 1, 3. This is one option, clearly. Another option is that this is one other option. No other options is correct. I don't know whether it is clear to you or not, but main point is that whenever you have two minimal polynomial, I mean you have minimal polynomial and you have two factor irreducible harmonic factor, then in the rational canonical form, not Jordan canonical form, in the rational canonical form, corresponding to each minimal polynomial, corresponding to each irreducible factor, you will have a component matrix. That is the first place. Second place is that they will be other component matrix will be corresponding to the polynomial of lower degree. Okay, of those polynomial but lower degree. But here is the only possible lower degree is 1. So that is itself it will appear. So that means either it will be, but at least they will appear at least 1. So that's why this will always will be there. This will always be there. So either repetition will be for this or repetition will be for this, because I need the 6 cross 6 matrix. That is what it is, the target. So is it clear? I don't know. This is a little tricky. So let's go to the another problem. I hope this problem will be more simpler at least. So here it is, another problem. So what it says, we have this, all these factors are there, the cyclic dimension, everything is there. So okay, let's see still. Let V equals to R for R, that means the vector space of dimension 4 over real R. And T is the operator which is given by this. Let alpha is equals to 0, 1, 0, 1. Then define the subspace Z alpha T, that is the T cyclic subspace generated by alpha. Alpha. So then the dimension of Z alpha T. Here it is asked the dimension of Z alpha T. So we know the dimension of Z alpha T actually the degree of the corresponding T annihilator, but we will not go to this direction. So Z alpha T, as I have said, Z alpha T is actually ft alpha, such that f of x is coming from the polynomial over real field, and this is equals to, if you remember here above, this is equals to t to the power k alpha, such that k is actually a natural number, that including 0. So basically I can write it as z plus. So I think 0 will also be included. Above I have written somewhere this fact, but I don't know what I have written. The k is in z plus. So this is what it is. So let's see. So we have alpha. Alpha is actually here. Alpha is equals to 1, 0, 1, 0, 1. There it is. This is the alpha, and t is actually t x1, x2, x3, x4. This is actually equals to x1 plus 2x2 plus x3 comma x2 plus 2x3 plus x4 comma x3 plus 2 x4 plus x1 comma x4 plus 2 x1 plus x2. This is what it is. So that means t will map 0, 1, 0, 1, where it will map 0 plus 2 times 1 plus x3, that is 2, and x2 will be like 1. Yes. Yeah, I of course understand that, but I can't speak here because this is recording and this recording will be checked by the NPTEL team. But I think you can say I will not bother you with it. Hmm. Yes. I think this is no, you will pass. That's not, their exams are not difficult. But I think the problem is that maybe these are the when it starts the primary decomposition from there, you may be little complicated. Before that, I think things are not that much tricky. But primary decomposition theorem, from primary decomposition theorem, this will be problematic. I mean, from primary decomposition theorem, you need little. I mean, you need to understand little more carefully. From primary, the main building block is that from primary decomposition theorem to the till cyclic or Jordan canonical form. That's the main target, is to give the simpler form. I believe I understand that maybe you are not able to understanding this clearly, but I can explain it, that actually there is no harm to explaining it more generally, because I am supposed to clear any doubt you, or any doubt you have. Okay, so I can little bit elaborate here. But that's actually a very good book. No, that's very good book, and I hope you may understand that's a simple book, not tough book. One day, I also similarly, in when I'm starting in graduation, that time also I also find it little difficult, but that book is very good and very good book actually. In fact, okay. So main target in this, in whatever it is there. So okay. So main target is that I can, okay. Let me one add one. Okay, I think. If it is not matching with the given answer, then okay. Assignment 9, you said, right? Can you say the questions number? Can you say the question number? Okay. Okay, I'll check if there is any problem. I think I'll be informing you. Huh. Okay. I'll check if there is any problem. I'll ask to professor to respond that matter. If it is there is a problem, if I inform them, then they may remove those problem from the assignment, from the evaluation. They will not evaluate those problems. Okay. Okay, so let's understand this, and after that, I will try to explain once again what is the primary decomposition, what is the cyclic decomposition theorem says. That may a little bit help you. Okay, so T0100, that will 01, that will go to like that will be 2, and another term is that x2 is 1, x3 is 0, and x4 is 1, so this is 2. Another is that x3 is 0, x4 is 1, so this will be 2, and x1 is 0. And next is that x4 is 1, x1 is 0, and x2 is 0, sorry, x4 is 1, and x1 is 0, and x2 is 1, so this will be 2. So this is what it is we are getting. So next is that t square 0 1 0 1, so that will be like t, this is suppose alpha 1, this is alpha, and this is t alpha, this is t alpha, and t square alpha is actually equals to t 2 2, that will be like 2 plus 4 plus 2, that will be 8. Always it will be 8, because all the formula are same. Just replacing x1 x2, interchanging x1 x2 x3, and here x1 x2 x3 is same. And this is exactly equals to 4 times 2 comma 2 comma 2 comma 2, that is equals to 4 times t alpha. So what we got, t square alpha is equals to this, that means t cube alpha, that is equal to t of t square alpha, t square alpha, that is equal to t of 4t alpha, that will be equals to 4 of t square alpha, and that will be 4 of t alpha, that is equals to 16t alpha. So whatever the power we may give tk alpha, if k is greater than equals to 2, then tk alpha will be either in terms of alpha or t alpha. That will be either or in linear combination is in linear span of t alpha and alpha. This is what it is. Basically what I'm saying, t3 alpha is able to express this in terms of t alpha. T to the 4 alpha will also be able to express this in terms of t to the t alpha. So that what my point is that this space is actually this space t to the power ft alpha, which I am saying that tk alpha for a k belongs to z class. This is actually generated. This is same with span of span of alpha and t alpha. This is what it is. We are able to prove. So that is z alpha t is actually span of alpha and t alpha. But note that what is alpha? Alpha is actually 1 0 1 0 0 and t alpha is actually 2 2 2 1. Clearly alpha is equals to 0 1 0 1 and t alpha, which is actually 2 2 2 2, are linearly independent. They are linearly independent. You can easily check. Linearly independent. That is, this is a basis of z alpha t. So main point is that so that is that the dimension of, I think this is what it is asked to find, dimension of z alpha t, that is equal to 2. So I hope this is the question. Then dimension of z alpha t is actually 2, and so all other options are automatically incorrect. So let's get back to the what is primary decomposition theorem and what is cyclic decomposition theorem, what is this cyclicity, and what all these things trying to say till now. So let me explain once again. Okay. So what I will be some little explanation. I'll try to explain it for a little bit so that you may understand, because that is your problem. So it's supposed to I supposed to explain it. So at least whatever you, let's try to focus how these things goes. So first is that our target is, we have started what is the definition of diagonalizability. That means diagonal, if you have a matrix T or operator will not distinguish, because always we will be writing the linear operator on a finite dimensional vector space, and that means that has a matrix representation, and two matrix representation corresponding to different bases for a linear operator are similar. So our target, so T and matrix will not be problem. So our target is actually to express T in terms of very simpler form of matrix. Now, what is in terms of this is means similarity, up to similarity. That means whatever the form I will give or simplest form I will say or trying to find, that is actually something similar to. Suppose we have a matrix T, we have a basis beta 1. So we have a matrix representation T beta 1, and another basis is T beta 2. So whenever we are saying the matrix and linear operator same, that means they are similar. We know that if we are taking a linear operator T and taking two bases on a finite dimensional vector space, two bases beta 1 beta 2, then matrix representation is similar. Okay, so that means our target is actually finding a simpler form of the matrix or finding a basis beta 1 with respect to which the matrix representation of T will be very simplest form. This is what it is target. And then we will say that whatever the basis we consider, T is actually similar to that simplest form. Okay, something like diagonalizability. What is, suppose you have a matrix T which is not diagonalizable. Okay, not always diagonal, but this is also not always diagonal. If it is diagonalizable, that's the most simplest form. But if it is not diagonalizable, then there may exist in simplest form. Suppose I have writing 1 0 0 1. This is also simplest form, but this is not diagonalizable. So now, if you have a matrix for which you can write it like this way, for example, if a matrix for which the minimal polynomial is x square, x minus 1 square, minimal polynomial is x minus 1 square, for that matrix the simplest form will be look like this way. If a matrix for any matrix for which the minimal polynomial will like this way, the simplest form of that matrix is look like this way. So if it is diagonalizable, then that's good. But if it is not diagonalizable, then we can't drop the hope that okay, that is the, we have to try to find the simplest form, which may appear, which may contains the maximum number of zero. This is the most target. Okay. In diagonal matrix, that is the except diagonal all entries are zero. But if it is not diagonalizable, then there we may find a matrix for which diagonal entries will be non-zero, but some more element will be non-zero, but maximum element will be zero. So that is the main target. So one thing we know that if we have a vector linear operator T from vector space V to V, and suppose we have two subspace W1, W2, and W1 direct sum W2, and they are invariant. They are invariant. W1 is subset of W2, and W1 and W2 is subset of W2. So then, if we try to find the matrix representation of the vector space T of this vector space V, then matrix representation will be actually this one. First of all, let's understand whether did you understand this one or not. Then we can go ahead. Otherwise, this is not possible to go ahead. If it is not understood, I will try to explain why this happens. This happens because you can consider a basis here, you can consider a basis here, and you can combine them to get a basis from vector space V. Now, those basis element from W1, they will map to W1 once again. So that's why, suppose we have here we have, suppose we have two element alpha 1, alpha 2, and here we have three element beta 1, beta 2, beta 3. So the total basis is no, I'm not saying that direct sum is not necessarily no, yeah, direct sum will be direct sum W1 direct sum. I'll be, yeah, W1 direct sum W2 is equals to V, because this is what it is, our target. So if we have basis alpha 1, alpha 2, beta 1, beta 2, beta 3, then collectively beta 1, beta 2, beta 3, this is the total basis of V. Now if I write T alpha 1, that will be something like C11 alpha 1, C12 alpha 2, T alpha 2, because T alpha 1 has to belong to W1. So that means that will not be in terms of beta 1, beta 2, beta 3. Similarly, T alpha 2 will be like C21 alpha 1 plus C22 alpha 2, and T beta 1 will be C33 alpha, no, beta 1 plus C34 beta 2 plus C35 beta 3, all these. So that means if you write the matrix, so this will be like alpha C11, C12, all other entry will be 0. Next will be like CT1, C12, all other entry will be 0. And here, as we don't have alpha 1, alpha 2, alpha 1, alpha 2, so these entries will be 0, and this will be C33, C34, and C35. So this will get, so this will be 0, 0, this is, so this is what it is the purpose. So that means this is we are one step ahead to the simplest form. We get plenty of 0 8. Okay, we get a plenty of 0. So basically, if we have this type of decomposition, then we can get. So now the primary decomposition says that if we have a minimal polynomial, suppose P, which is actually decomposed like P1 to the power R1 all the way Pk to the power Rk. Okay, so primary decomposition theorem says that this is a theorem. So I am not going to prove this theorem, but I will try to explain using those theorems how the simplest form we are going. You have to understand, you have to read this theorem and proofs from the book. Okay, so thing is that here I will consider W1 actually kernel of P1 P to the power R1. So for simplest form, you can consider this is something like x1 x minus c1 to the power 2 x minus c2 to the 2 to the power 3, something like that, for to understand, to connect it. So that means you are here considering kernel of, here you will be considering kernel of t1 minus t minus c1 I square. Kernel of, note that this is the minimal polynomial. Once we have the diagonalizability, that is if and only these powers will be 1. Minimal polynomial will be completely distinct product of distinct factor. That is the theorem for the diagonalizability. So that's why this should be completely distinct product. This should be completely distinct product. But in that case, this is the kernel of t minus c1I. Then that is means the eigenspace. That is exactly the eigenspace whenever you have diagonalizability. Okay. But we may have the minimal polynomial for which the minimal polynomial for which the power need not be 1. Okay. That means that, and you can consider another factor x minus c3, something like that. And c1, c2, c3 are distinct. So that means here W2 is actually to kernel of P2 to the power R2 T, and this is, so here it is in kernel of P minus C2 I cube, and W3 in this case will be kernel of P minus C3 identity. So that is exactly the eigenspace. Okay, exactly the eigenspace. Correspond. So basically, you know that you have whenever you have the linear factor, no power, C3, C3. I'm talking about the each of the. Here is the. This is the P1. This is P2. This is P3. I'm just giving you the parallel example. This is the minimal polynomial. Okay. Okay. This is the general minimal polynomial I'm talking about. For now, assume that P actually look like this way. So in parallelly, I'm trying to explain you what is the kernel basically. Okay. Okay. Let me clearly write it. And W3, which is actually equals to kernel of direct subspace. That I'm going to, yeah, W1 W plus P3 R2 R3 T. So for example, here I'm saying what are the actually corresponding to these three elements I'm talking about, corresponding to parallelly C3 this is. So primary decomposition theorem says that W1 direct sum, W2 direct sum, they will be orthogonal, and this direct sum will be full space vector space V. Note that whenever you have diagonalizable, so in that case these powers are 1, right? This is what it is the theorem says. In that case, these Wi's are nothing but the kernel of T minus C1i. That means the eigenspace corresponding to Ci's. And that is what it is we mean by diagonalizability. That V can be written as the direct sum of or we will have a basis which will span the we will have a basis consisting eigenvectors which will span the vector space V. This is what it is mean by diagonalizability. I mean, I'm just trying to say that diagonalizability is not violating. Diagonalizability is following from this primary decomposition theorem. This is what I'm saying. Okay. So whenever it is not diagonalizable, our target is obviously for non-diagonalizable. So in that case, the minimal polynomial V will be can be written like this. So in not only this each Wi is actually invariant under T. So whenever it is invariant, we can restrict T to this subspace and we can consider it as a linear operator from Wi to Wi. This is itself a linear operator. For this linear operator, the minimal polynomial is Pi, whatever the corresponding this one, Pi to the power Ri. Okay. And one point I must point out, whenever you have minimal polynomial look like this, the characteristic polynomial will also be look like product of Pi to the power some Di, where Di's are actually greater than equals to Ri's. Ri's. Not always we will have this linear factor, but here we may have the monic polynomial which are not linear. Like the previous example, like the first question, there is the x cube minus x square minus t square minus 3t plus 4. They are not factorable in real number, but in complex they will be factorable. In complex, every polynomial is completely factorable. That is the algebraically closed field. That's why you can factor it in linear factors. Power can appear, some power can appear, but you will have the linear factors. Okay. So characteristic polynomial will be look like this, but I don't need right now the characteristic polynomial. So now as these Wi's are invariant and W can be written like this way, then like the previous I have said, whenever you have invariant subspace and V direct sum of W and W to W3, then we can express the matrix representation with respect to some basis. That basis is corresponding to the basis of W1, W2 and W3 collectively. You collect the basis of W and you collect the basis of W2 and collect the basis of WK and take their union and construct that is a basis of this, and then the matrix of T will be the this way. I have said this up to this point. I hope it is clear, right? Okay, so let me give you 1 second. 1 second. Now our target. So we will be getting 0, 0, 0, and here is some non-zero. So we get a specific block form. Now our target will be to find the more simplest form of this matrix. So basically, what will be? Let's consider instead of this Wi. So basically, we have considered that T restricted to Wi from Wi to Wi, right? So for this, the minimal polynomial is Pi to the power Ri, right? So we will be focusing a linear operator T from the vector space V to V, for which the minimal polynomial is actually P to the power R or P to the power N, where it is what is the notation given, and P is actually irreducible monic polynomial. I mean, basically what we have changed the task right now. Task is that t, actually we can consider t raised to wi as a operator from wi to wi, for which the minimal polynomial is pi to the power ri. So now here, so instead of looking this, let's restate the questions that t is a linear operator from the vector space V to V, for which the minimal polynomial is p to the power some n, and p is actually irreducible monic polynomial, because these are the building block in primary decomposition theorem. Primary decomposition theorem, these pi's are actually irreducible monic polynomial. So that's why we will be focusing on this. So in particular, parallelly, you can consider that Cj eigenvalue. Just 1 second. Hmm. Yes, can have, not necessarily. Irreducible means that x minus c itself is an irreducible polynomial. Okay, but x square minus 2x plus something like that c is there, for example. That does not say that eigenvalue is not there. This is irreducible. This, both of them are irreducible, but this is not irreducible. But note that this no. These are the bases, na? We can arrange and construct the bases. They are not eigenvalues. First of all, they are no. Okay, sorry. What I'm saying, these wi's are not eigenspace. First of all, okay. Wi's are not eigenspace. They are reducible. They are reducible corresponding to t. They are reducible. Hmm. Obviously, of course, of course. So that's the purpose to give the primary decomposition theorem. So that's why you are getting. So that's as primary decomposition theorem says that like this way. So our target is to give simplest form of each of the block, right? So let's restate the questions that T is a linear operator from the vector space to V to V, for which the minimal polynomial is P to the power n, and irreducible monic polynomial. P is an irreducible monic polynomial, because these are the case whenever these are the simplest case. This is the, if we know the answer of this, then we can express this one. We can, each block can be simplified. This is the target. Okay. So now target is the P is irreducible monic polynomial. Then how to, then what is the, suppose we have this fact, then how to get the simplest form of the matrix? This is what it is target. So to get this, to fulfill this target, so what we have to go? We have to go through the cyclic decomposition theorem. Cyclic decomposition theorem says that you just start with the fact that let's alpha is a vector which is not equals to 0. Alpha 1 is a vector in V. Okay. Let's consider z alpha 1 comma t, that is equals to t to the power k alpha, span of t to the power k alpha. K is coming from z plus t. Now note that V is a finite dimensional vector space, for example, right? So then alpha, t square alpha, all the way, whatever it is, it will always be, after some time it has to be repeat. It has to be going to 0. Basically, we can't have the infinite. Here it will be finitely generated. Here it will be finite generated. At V is finite dimensional, as V is finite dimensional, this will be finite dimensional. Why? Because another way you can look at, because you have a minimal polynomial. Pi is to the power ni minimal polynomial. That means P, this alpha has to be 0, because P nt is 0. So this is a polynomial, it has degree, right? So that means the highest degree, whatever the highest degree will be, suppose the highest degree is, suppose P is polynomial of degree k, then highest degree will be nk. So that means t to the power nk alpha can be written in terms of lower powers, right? And whatever the any power which is greater than some something like some any other, that will also can be written in terms of power less than equals to. So that's why it will be finite dimensional. So you get a finite dimensional subspace. Okay, this is a subspace of V, and interestingly, this is something like that. We have alpha, t square alpha, t to the power some k alpha, right? T to the power k1 alpha. So first, basically consider this is actually span closure of, not closure. Uh, Basically, this is something like, assume that alpha 1, t alpha 1, t square alpha 2 all the way t to the power k alpha 1, right? K minus 1 alpha. So this will correspond to a polynomial which is called p alpha, which is a k degree polynomial that is called cyclic T annihilator. Okay, I'm going to little separately that. Now we have alpha 1 is exhausted. Now this space, clearly this space is linearly uh, reducible under T, because if you act T on alpha, that will go to T alpha. It will go, if you act T on T alpha, that will go to T square alpha. T square alpha 1. And in this way, if you go to act T on this T to the power k minus 1 alpha, that will can be written in terms of linear span of all the vectors. No, T to the power k alpha is not necessarily 0. T to the power k alpha not necessarily 0. T to the power k alpha can be written in terms of linear span of all of these vectors. Yes, no, T to the power n alpha is also not good. What I am saying, suppose P is the matrix, for example, x square minus x plus 1. This is the P. Okay, we have square. For we can assume, for simplicity, we can assume 1. Okay, suppose this is the one. So basically, we know that T is equals to 0 because this is the minimal polynomial, right? Minimal polynomial is that polynomial which will annihilate the operator. That means T square minus T plus all identity is equals to 0. That means T square minus T alpha plus alpha is equals to 0. That means T square alpha can be written in terms of T alpha and alpha. So that means T to the power k alpha, here k is 2 right now. Okay. T to the power k alpha can be written in terms of alpha T alpha. This is something like, T to the power k alpha can be written as a linear combination of alpha T alpha T to the power k minus 1 alpha. That is what it is. So that's why, so that means this space is, and any power, any bigger power, that again can be written drop down, we can go drop down to this space. So that is invariant subspace, right? Now let's take another vector alpha 2 which is not in vectors V but not in this space. Span of this space, or basically you can write it as Z alpha 1 T, right? This is what is the purpose of cyclic decomposition theorem. So we can again construct Z alpha 2 T, because alpha 2 is not here. Alpha 2 is not in Z alpha 1 T. Alpha 2 can't be written as in terms of Z alpha 1 T, right? So now we have Z alpha 2, right? We can again construct the cyclic subspace like this way, corresponding to alpha 2 comma T, right? That will have that way some up to some power. That power may vary. That power depends on alpha 1, right? Because minimal polynomial is the biggest, but it can be for lower. Here it is means for it is a polynomial for which it will send every for every alpha it will be alpha is equal to 0. But there may exist smaller degree polynomial which will send only for this specific alpha. My point is that if you have minimal polynomial, this one, for example, minimal polynomial is x minus x plus 1 square. So that means this T alpha is equal to 0, whatever alpha I may take from the vector space V. But whenever I am taking a specific vector alpha from V, for this vector, there may be some lower degree polynomial. Which will divide this polynomial. That is what is called P alpha 1, which will be making this alpha 1 equals to 0. Only this specific alpha 1. That will definitely make to 0. And whatever the degree of this polynomial, that will be exactly same with k. Here is the k. That is what it is, the k. That's why this is the, and that polynomial is called the T annihilator, corresponding to alpha 1. Annihilator means which will send to 0. T annihilator is that smallest degree polynomial which will send alpha 1 to 0. Of course, minimal polynomial will send, but there can be a smallest degree polynomial, because I am looking for minimal polynomial, right? So that's why we will be looking in the smaller. Yeah, for particular vector we can get the smaller degree polynomial, right? In fact, you can check for this one, this 0 1, sorry, 1 1 0 1, for which if you consider 1 0 0 1 0 1 vector and 1 1 vector, or either 1 0 1 1 vector, then you will get different, maybe I believe maybe different. For this maybe you will get, I mean, these are the vector, this is vector, you may get different polynomial which will annihilate those things. Okay, so this is the purpose. So that's why that specifically depends on k1, depends on alpha 1, right? And now we can consider alpha to another vector which is not in the, I mean, there always exist. If for example, if there is no such vector, alpha 2, that means z alpha 1 t is actually the vector space V, right? If there is no such vector alpha 2, okay? So that means the vector space V will be cyclic, and in that case, that is exhausted. We don't need to do. I mean, in that case, the matrix representation of T with respect to V will be component matrix corresponding to this. Okay. Here I just want to point out, as I have said, I am taking Z alpha 1 T, and there exists a smallest degree polynomial, monic polynomial, that is also be irreducible, smallest degree monic polynomial, P alpha 1 of degree k1. This is alpha 1 just denoting k1, such that P alpha 1 T alpha 1 is equals to 0. That will come from that P annihilator ideal. Okay, I am not going to that. But interesting fact is that this is equals to, in that case, span of alpha 1 T alpha 1 all the way Tk minus 1 alpha 1. And as I have said, this is the invariant subspace. I am not going to discuss how this is connecting to this, but corresponding to this alpha 1, whatever the T cyclic subspace I will consider, that cyclic subspace will be generated by this k vector, and this is corresponding. One side will give other, something like that. There exists a smallest reducing subspace, smallest degree monic polynomial of degree k1, which will send this one. And if the degree is k1, then this space is actually generated, spanned by this, and these are linear vectors. So now, as I have said, this is invariant under T, right? Now, if we don't have any other vector, suppose alpha 2 is vector V, I am removing, taking complement of the subspace. I mean, I am removing the Z alpha 1 T from the vector space V. Okay, there must exist a vector space. There must exist an element alpha 2 from V, okay, which is not in the span of. I mean, basically, this means that there exists alpha 2 in V such that alpha 2 is not in Z alpha 1 T. If there is no such alpha 2, that means if there is no such alpha 2, that means V is actually equals to Z alpha 1 2. Is this clear? Is this fact? Before going to alpha 2, I am just trying to say that if there is no such alpha 2, that means there is no vector which is not in the span of Z alpha 1 2. There is no such vector alpha 2, that means V is actually the full space. V is actually Z alpha 1 2. For this space, as I have said, this is invariant subspace, and the matrix representation of T with respect to this invariant, I mean, restriction of this is invariant subspace. That means I can consider linear operator T on this subspace, right? Now we will have a basis of this space, and that is literally this basis, alpha 1 T to the power k minus alpha 1, such that the matrix representation of this with respect to that basis will be the companion matrix for this polynomial. That is like 0 1 0 0 0 0 1 like this, and this will be minus C0 minus C1 all the way minus Ck minus 1 whenever if P alpha 1 at the point x is equals to C0 plus C1x plus all the way plus Ck minus 1 x to the power k minus 1 plus x to the power k. This is a polynomial of degree k, that means that must be of this form. Then there must exist a basis, and that basis is literally this one, alpha 1 T square alpha 1 T to the power k minus 1, for which the matrix is like this way, that is the complement matrix. So in that case, if this happens, then the matrix representation with restriction on V or Z alpha 1 T, whatever, this is same. If I assume there exists a basis with respect to the matrix representation will be companion matrix. This is called companion matrix. Minus C0 minus C1 all the way minus Ck minus 1. This C0 are this polynomial, and this is the annihilator polynomial corresponding to alpha 1. Okay. Now, if suppose V is not equals to Z alpha 1 T, that means there must exist a vector alpha 2. then we can consider z alpha 2t, right? Corresponding to this, there exists a polynomial p alpha 2, which is called the annihilator polynomial. That will be like c naught dashed plus c1 dashed x plus all the way c k dashed minus 1 x to the power k dashed minus 1 comma x to the power plus x to the power k dash. Some different index I'm trying to say. K dash means different index, c naught dash means different from here, different from this c naught c1, something like that. So now this will have, I mean, this z alpha t will be similarly like the z alpha 1 t is invariant under t. Similarly, z alpha t will be invariant under t. But note that V is finite dimensional vector space. But we can't get this alpha 1, alpha 2, alpha t such that this will be always getting some z alpha I t. We must have somewhere we will be exhausted. That means the vector space V can be written like this direct sum z alpha 1 comma t, direct sum z alpha 2 comma t. Up to some point it will go, but after some point it has to exhaust because this is finite dimensional vector space, right? And I am itself taking alpha 1, alpha 2, alpha non-zero vector. This is also non-zero vector. So that means at least each of them have dimension 1. So that means they must at least exhaust some point, right? So this is what it is called the cyclic decomposition theorem. And as I have said, each of the spaces are actually invariant under T. So that means matrix representation of T with respect to this V with respect to this decomposition will be T restricted to Z alpha 1 T, T restricted to Z alpha 2 T, like this way it will go. Note that. Now let's recall. We have primary decomposition theorem, the W1 direct sum W2 plus WK, right? And corresponding to the minimal polynomial P1 to the power R1, P2 to the power R2, Pk to the power Rk, and where Ti are actually restricted to Wi, the minimal polynomial actually corresponding to Pi to the power Ri. Now, this cyclic decomposition theorem I have started with the fact that irreducible monic polynomial. And with respect to this decomposition, we have the matrix like T restricted to W1, T restricted to W2, and like this way. Now, corresponding to each of them have this type of decomposition, this cyclic decomposition, because cyclic decomposition is for irreducible polynomial. I have started for irreducible polynomial. Here I mean, cyclic decomposition for non-irreducible is also there, but we have started for irreducible. That's so. So this is the way we can get and recall that this linear operators has the matrix representation that is companion matrix corresponding to these polynomials, right? So that's why these are simplest form. Now I'll be a little bit of going to the Jordan canonical form. So basically what I got, basically I will be getting like these type of blocks. These are the corresponding like W1. Let's be in two cases. This is in W2, corresponding to the primary decomposition, right? And each of them are corresponding to breaking to like Z alpha 1 T, corresponding to this breaking, right? T restricted to Z alpha 2 T, like this breaking. Here is will be T restricted to Z some other vector beta 1 T. These are the breaking, and each of them are actually component matrix. And component matrix key, because each of these Z alpha 1 corresponds to a polynomial, right? That is what's called the T annihilator. And the component matrix for a polynomial, if I write C1 C naught plus 1 plus Ck minus 1 x to the power k plus x to the power xk minus 1, and it will be like x to the power k, then component matrix for these actually 0 1 0 0 0 0 1 0 0 minus Ck minus 1. That means these are the matrix will sit here. I mean, they are not same. They can be same, but I'm not saying they're not necessarily same. But these are the depending on polynomial. That's the going to the simplest form. Now, whenever I'm saying, whenever you have the primary decomposition, here is the primary decomposition. Suppose we have complex field. In that case, every polynomial is actually factored into linear factors. So in complex field, whatever the minimal polynomial it is, that will always be factored like this way. Because in complex polynomial, the linear factors are the only reducible factors. There is no degree to factors. Okay, so that means here P1 to the power m1, that is actually nothing but x minus c1 to the power m1. P2 to the power M2, that is nothing but x minus C2 to the power M2. Like this it will go. So for example, right now take 2, 1. Now corresponding to this has W1 subspace, corresponding to has W2 subspace. Now here is, if you recall, when in the previous class, when I am trying to explain what is Jordan canonical form, whatever the information in Jordan canonical form, there I have said we have to take one block corresponding to this C1, C1, 0, I think C1, 1, C1, 1, 0, 0 like this, 0, C1, 1 of order M1 by M1. There is another theorem which I am not going to discuss today. So this P1 is actually corresponding to this factor. Okay. So now corresponding to this P1 and W1, this pairing. So here we will have this cyclic decomposition, some factor up to some factor. Okay. So now this one will correspond to the minimal polynomial corresponding to this first one. First one will be for which the what is called the component matrix will be T annihilator will be T M1, and all other T annihilator corresponding to this, they will be P1 to the power some other power, but this other power is actually less than equals to M1. There is, I mean, here I am saying that P alpha 1, right? Here I am saying P alpha 1 and P alpha 2, all these, they are actually power of this same minimal polynomial P. We have what we have started, that P to the power n. They are actually power of that polynomial, nothing else. Okay, so that means so this, suppose this P1 is, suppose M1 is equals to 2, M1 equals to 2. That means the first factor corresponding to this will be x minus C1 whole to the power 2. Next one will be either x minus C1 to the power 2 or x minus C1. Next one will be either x minus C1, I mean, if it is x minus C1, next one is only possible x minus C1. There is no other possibility there. But whatever the next one will be, that will be like if it is power is actually this first P1, PM1, Pn1, all the way Pn, suppose this is K, not K, this is something different index I should give. Some P, not P, R, then this NR, then this N1 has to be exactly N, and that is R1, which I have taken primary decomposition, and all other will be less than equals to NR, something like this. Okay. So now corresponding to this component matrix is actually, that is somehow connected. I am not going to discuss because that component matrix of nilpotent matrix corresponding to this, that if we consider n is actually T minus C1i, then n square. For this the component matrix is actually 0, 1, 0, 0. Now n is actually equals to T minus Ci. Suppose this is the n expression of n. So that means expression of T is actually C1, 0, 1, C1. So this is the first block. All other block will be less than equals to of 2 order block or 1 order block. That's how the Jordan canonical form comes. I hope at least up to this point, I hope it is clear up to how this decomposition goes. So if possible, then I will in the next class I will try to explain from here how the Jordan canonical form goes. Up to this point, I hope clear. So one fact I have not mentioned properly, that is that here we have corresponding to this W1, I have said P1 R1 is the minimal polynomial. So we will able to find a vector alpha 1 for which the T annihilator will be P1 to the power alpha 1, and consecutively all other alpha 2, for those the T annihilator will be P to the power some other powers, but those powers will be less than equals to alpha 1. Okay, the same polynomial P1. Okay, so I hope up to this one how the things go simple. I hope it is clear, right? So let's go to some problem. So now you start. Okay, you have to start a study and start to study the Hofmann-Kunz itself. And if you have any doubt, you can ask me. I'm here. Or even in discussion group, there some other member will also may help you. Okay, so let's look at this problem. So let's go to at least one inner product problem. So what this is inner product. I'm not going to discuss inner product. I hope inner product is simplest thing. If it is not clear, I can again discuss. Inner product is actually, suppose you have a vector space V over a field A. We have to give a map from V cross V to the field A such that it will be linear in first one and antilinear in the second one if it is in complex field, and it will be like alpha beta bar is equals to beta alpha, and it will satisfy the fact that inner product alpha is actually strictly greater than 0 if alpha is not equals to 0. If alpha is not equals to 0. Yes. I mean, I have attached, no, I have attached those problem in the previous class. I have attached those problem in the previous class as you asked. Whatever remained, I am not able to solve that. Whatever I am doing, whatever left to me, I am attaching those problems. Okay. So, so this is the third problem, but okay, I have explained in between whatever it is. Okay, so here is the vector space. So here is a very interesting theorem. So let me quickly say that we have a vector space. Let T from the vector space V to W and be a linear operator. Linear operator, and another thing, this video is going to be uploaded in YouTube. So it's try to be, I mean, if it is not possible, somewhere you are not stuck, not able to speak in English, that's okay. But I hope no one will complain. But I am not. That's why I'm not saying anything. But you can speak. But it's better to try to understand, try to speak English. If it is not possible, you can speak whatever you want. That's not a problem. I'm not saying, but it's better to try to as much as possible. That's what it is. My point. Let T be a linear operator. Let T from V to W be a linear operator, and let W. We have a WBA inner product. Let W be inner product space, but we don't know any inner product structure over V. So inner product actually just a special structure on the vector space. We have a vector space over a field. Now we are giving something additional to that vector space. That is what it is, inner product. But vector space can appear without that inner product, right? So inner product space is actually a vector space with some additional condition, which should satisfy linearity and linearity of all these things. Okay. So now W is a linear inner product space. Now if T is injective, that is what it is called, that is T alpha is equals to 0 should imply that alpha is equals to 0. Okay, then we define an inner product. We don't know any structure on V. We know only V is a inner product space. We have an inner product on V, but we don't know any structure on the vector space V. On V, by this, for any alpha and beta in the vector space V, inner product alpha beta I'm indexing by V, that is actually giving by T alpha T beta, that is on W, because T alpha T beta is element in W, so that's why I can give T alpha T beta in W. So now as T is a linear operator, this will satisfy the fact that linearity in the first component, we can check the linearity in the first component. This will be equals to T alpha 1 plus C alpha 2 comma T beta, that is in W. So T is a linear operator, this will be T alpha 1 plus C T alpha 2 comma T beta, and this will be, as T is linear, and W, right now I will be using the fact that inner product in the W. So as it is inner product in W, so it will satisfy this fact, because this is the linearity in inner product in W. So this is going to be alpha 1 inner product beta in V plus C into alpha 2 inner product beta in V. So this way we get the linearity in the first component, and we will get the antilinearity on the second component. I will not go discuss that. But the important fact is that here I have, if you point out that here I have taken injective. Injectiveness I have taken because if you take alpha is a non-zero vector in vector space V, then T alpha inner product alpha inner product alpha in the vector space V, which is actually nothing but T alpha in the space V, in the space W. Now if it is inner product, then we should have alpha not equals to, for alpha not equals to 0, this has to be greater than 0. But if T is not injective, that means there may exist a there exists a vector alpha which is non-zero, but T alpha is equals to 0, that will become 0. But I need that has to be not equals to 0. But that is not equals to 0 if T is injective. This is not equals to 0. In fact, this is positive as T alpha is not equals to 0 in the vector space W, and any vector gamma in W, we know that gamma inner product gamma is greater than 0 for any non-zero vector, right? So that's why as T alpha is non-zero, an element in W will have positivity. So this is one of the important facts. So that's why we need to T injectivity is needed. So if we are giving a linear operator T which is not injective, and you are asked to define that whether this is an inner product or not on the vector space V. The answer is no, that is not an inner product, because that will fail to be an inner product at this point. That will fail to satisfy this property. If alpha is non-zero vector, then alpha inner product alpha alpha has to be positive, that this condition will be failed, because if T is injective, T is not injective, there will always exist a vector alpha which is non-zero such that T alpha is equal to 0. Now for that case, T alpha inner product has to be 0, and which is actually defined as alpha alpha. So that means alpha being non-zero, inner product alpha alpha is 0, but that violates one of the important property of the inner product space. So that will say that we will not be able to have the inner products. So let's go back to the problem. So here the problem is that W is actually V the vector space. V is actually the vector space R3 over R. I hope it is over R. Yeah, it is over R. And we have polynomial W is actually equals to P2R. Okay, that is the space of all polynomials. C0 plus C1 x plus C2 x square such that C0, C1, C2 are real number. This is what it is. Okay. Now let's T be a linear operator from R3 over R to P2 over R, that is given by sending any element C0 or any element like alpha 1, alpha 2, alpha 3, that will go to that alpha 1 plus C1 alpha plus C2, alpha 1 plus C1 x plus alpha 1 plus alpha 2 x plus alpha 3 x cube. Let me check this is I'm writing correctly. Yeah, x0 x1 t, that is what it is. So now let's define a inner product like alpha 1 alpha 2 alpha 3, inner product with beta 1 beta 2 beta 3, two vector, that will be equals to inner product of alpha 1 plus alpha 2x plus alpha 3 x cube, inner product of beta 1 plus beta 2x plus beta 3 x cube, sorry, x square. I'm really sorry, this is x square. So these are two, and this is what it is. This is in vector space V, and this is in W. This is in not vector space V. This is in R3 over R, and this is in P2 over R. Okay, I need 2 minutes break. I'll be back again. Yeah. So what it is, the inner product given actually. Inner product is actually giving as the inner integration 0 to 1 alpha 1 plus alpha 2 t plus alpha 3 t square beta 1 plus beta 2 t plus beta 3 t square dt. Okay. So I have to first find what is this product. That is actually alpha 1 beta 1 plus what is the coefficient of t. Coefficient of t is actually from where I can get the coefficient. This is the constant term, that's true. Coefficient of t will be like alpha 2 beta 1 plus alpha 1 beta 2. This is what it is. Coefficient of t square, what it will be? Coefficient of t square will be like, let me just product it first completely, then I will be separated. So this will be like alpha 1 beta 1 plus alpha 1 beta 2 t plus alpha 1 beta 3 t square. Okay, what is the question? Question is, I think, it is x0 x1 x3, so I have to find it completely. So instead of this, I will be x0 x1 x0 x1 x2, and okay, x1 y1 z1 x2 y2 z2, that is what it is I have to find. So let's take this is x1, I'm changing the notations only, x1 y1 z1, this will be like x1 y1, so let's change it to the t then, t plus z1 t square. So it will be like x1 y1 z1 x2 y2 z2. This will be like x1 x2t x3, sorry, x1 y1 t, too much confusion, plus z1 t square. This will be like x2 y2 t plus z2 t square. This will be like x1 plus y1 t plus z1 t square, x2 plus y2 t plus z2 t square dt. So let me first find the product. So this will be like x1 x2 plus x1 y2 t plus x1 z2 t square plus y1 x2 t plus y1 y2 t square plus y1 z2 t cube plus z1 x2 t square plus z1 y2 t cube plus z1 z2 t to the power 4 dt. Now, so what will we have? 0, 1, x1, x2. Okay, okay. A constant term, let's collect constant term. x1, x2, this is the first constant term, and let's collect t term, that is x1, y2 plus y1, x2. This is, and what is t term? This is what it is, t plus. Let's collect t square term, that is first term is x1, z2, another term is y1, y2, and there is z1, x2. This is t square, and let's collect t cube term. T cube term, this is y1 z2 plus z1 y2 whole t3 plus t4 term, this is t z1 z2 t4, and we have to do it integration dt. So we know that this will be like x1 x2 first one, because it is in integration over 0 to 1. Next term will be like x1 y2 plus y1 x2, and integration of t will be t square by 2, so that will be by 2 here, plus it will be like x1 z2 plus y1 y2 plus z1 x2, and it will be integration of t cube t square, that will be t3 by 3, that's why it will be 3 here. Next term is t4, this will correspond to t4, that is y1 z2 plus z1 y2 by 4 plus z1 z2 by 5. This is what it is. So let me check which option is correct. Oh god, here it is. They have changed many things. So I have to take x1, y1, z1 common somehow. So if I take x1 common from this term and this term, this will be like x1, x2 plus y2 by 2 plus z2 by 3. This is like x1, x2 plus y2 by z2 by 3. This is x1 is done. Now y1, if I take common, that will be like x2 by 2. This is done. Next is, this is done, this is done, this is done, this is done. Next is, this is also done because x1 common. Y1 if I take common, this is done. Now if I take this one, that will be like y2 by 3. Now if I take y1 common, this is, it will also be there, z2 by 4 plus, if I take z1, this is x2 by 3 plus y2 by 4 plus it will be z2 by 5. This is what it is, and this is option B. I hope it is clear. If there is any doubt, you can ask, otherwise I will go to discuss another problem. This is a simple calculation you have to do, but there is a theory is that here for an inner product on the space W, if you want to convert it to the inner product on the space V, you need that injectivity. Otherwise you will not be able to convert those inner product. So let's go to the another problem. If there is any doubt, you can ask. Otherwise, in fact, later also you can ask. Right now also you can ask whatever you comfortable you feel. So here is another important question that is also important. Consider a vector W is in Cn cross 1. That means a column vector such that yeah, such that W star W is actually 1, and where star denotes the conjugate transpose. Let A is equals to I minus 2 times W W star. So note that W is actually Cn cross 1. So that means W star that will be in C1 cross N. So that means this is a column vector, this is a row vector. So that means W star W, that is and a complex number in C, there is no doubt. But W W star, this must be a vector in Cn cross N. That means a matrix of order n by n. So here A has been taken is equals to I minus 2W W star. Then which of the following statement is or are incorrect? First question is the Hermitian. So what is mean by Hermitian? A matrix A in MNC is called Hermitian if A star is equals to A, or called self-adjoint, where A star is conjugate transpose of A. That means we have to take conjugate of every element of A and take it transpose, or you have to take transpose and then conjugate every element. So this is called self-adjoint also. So this is Hermitian. What it is mean by Hermitian? This is Hermitian. So let's check whether here given A is that I minus 2 W star. So now here A is equals to this. So A star is equals to I minus 2 W star whole star, that will be equals to identity minus 2 W star whole star. But here is one fact. For any two vector, for any two matrix, for M and N belongs to M and C, M plus N star is just M star plus N star. But M N star, that is equals to N star M star. These are the properties of adjoint. I am not going to prove that. So basically it will be minus 2 times W star will be W star star and W star. That is equals to I minus 2 W star. So that is equals to A. So A is Hermitian. So first option is correct. Second option is that the column of A, just a minute. Just a minute, there is a okay, there is an issue, I think. Hello? Hello? Am I audible? My screen is not visible, right? Okay, just a minute. I don't know what happened. Yes. Yeah, I hope it will be visible now. Now visible, I hope, right? Huh. So this is A is Hermitian. Okay, I'm just recording. So first option is correct. A is Hermitian. Next option is the column of A form an orthonormal set of vectors in C n cross 1. So here is one fact I will be using, that is that if A is an invertible matrix, then the columns of A will be invertible. Okay. So if A is invertible, then columns will be, the columns of A are orthonormal set of the vectors in C n cross 1. Okay, here it is written W star W is equals to 1, that we know. How to use that fact? Okay, so here note that interesting fact is that A is self-adjoint, right? Sorry, Hermitian. Hermitian. That is A star is equals to A. Now, note that A square, which is actually A star, you can consider. This is equals to identity minus WW star whole into identity minus WW star. So this will be identity minus WW star minus WW star plus WW star WW star. But WW star is equals to, as it is giving, W star W is equals to 1, constant. That is already is mentioned in the question. So this will be identity minus WW star minus WW star plus, it will be WW star. So one factor will be cancelled out. That's true. Oh, there is a 2. Sorry, I'm not missing that 2. Yeah, there is a 2. That 2 will be helpful here. So this will be 2, 2, 4. So this will be 4 and this will be 2, 2. So this will be identity right now. So that is what I'm just obtained. A is self-adjoint. So A star A is equals to identity. A star A is equals to A square, which is equals to identity. That means A is an unitary matrix. Unitary matrix. We call that a unitary matrix is, that is A star A is equals to identity is equals to A star. This is called a unitary matrix. But it is self-adjoint, so that's why A star A and A star both are same. So now for a unitary matrix, it is known that for an unitary matrix, all the column vectors or row vectors, column vectors or row vectors are orthonormal. But first here I have not mentioned what is mean by orthonormal. Orthonormal. So what is mean by orthonormal? First know what is orthogonal. Orthogonal means, that is two vector alpha and beta. Suppose V is an inner product space. Let V be an inner product space and this is an inner product. This is the inner product. Is the inner product. Then two vector alpha beta in V is orthogonal. First orthogonal if alpha inner product beta is equals to 0, and a set and and a set alpha 1 all the way some alpha k in V is said to be orthogonal, said to be orthogonal to each other, if alpha I, alpha j inner products are equals to 0 for all I not equals to j, and called orthonormal set or orthogonal set. This is called orthogonal to each other or orthogonal set, and called orthonormal if in addition to orthogonality, if in addition we should have inner product of alpha I comma alpha I, that is 1 for all I equals to 1 to k. I hope you know these things, but still this is little formality we'll mention. So this is what it is meant by orthonormal. Orthonormal is means inner product of alpha I will be 1, and orthogonal means alpha I alpha j. I mean orthonormal S set is said to be orthogonal. It means that every vector will orthogonal to each other, and it's said to be orthonormal if every vector is orthogonal to each other as well as norm of the each vector is 1. So that means this is what it is, and we know that unitary matrices, actually there is also something we have to prove, then we can say, for an unitary matrices, all the rows or columns, if we take the set of rows or if we take the set of columns, that will be an orthonormal set. So this is also true. The columns of A form an orthonormal set of the vectors Cn plus 1. Oh, sorry. Here answer is which is incorrect. Which is incorrect. So that's why this is correct, and this is correct statement, but as an option not correct. This is correct statement, but as an option not correct. The matrix A is diagonalizable. This is also true. This is a theorem, I can say. I will not prove because I don't know how these questions are given, but this theorem will supposed to be at the end. But this is also mentioned here. Any normal matrix is diagonalizable. And square matrix, of course, the square matrix A is Mn, C is called normal if A star A is equals to A star. So in particular, any self-adjoint matrix is normal. Any matrix is normal. Not only that, any unitary matrix will also be normal. But self-adjoint is the bigger space. I mean, normal is the bigger class. Self-adjoint is the smaller class contained in there. And unitary matrix is another smaller class contained in there. But self-adjoint does not mean that it will be unitary, or unitary does not mean that it will be self-adjoint. Whatever it is, this is self-adjoint, so that's why it is normal. And a normal matrix is diagonalizable. So that's why this is also two statements, so not a correct option. So automatically the correct option is last one. But let's check whether that is the correct option or not. I mean that may fails to be correct or not. There exists some vector x in Cn cross 1 which is not in the linear span of column of A. That's not correct. As the columns of A, as the columns of A forms an orthonormal set. Okay, columns of A forms an orthonormal set, and A is an n by n matrix. Not only A, A is unitary. A is unitary. A is equals to I minus W2 WW star. Orthonormal set. Now look at A is an n by n unitary matrices. So that's why its column forms an orthonormal set. So if C1, C2 all the way Cn is are columns is a set of columns, then the C1, C2 all the way Cn is an orthogonal set, orthonormal set. In particular, it is orthogonal, and any orthogonal set is linearly independent. Those things I hope it is discussed in class. In particular, it is orthogonal, and it is known that is result theorem. Any orthogonal set is linearly independent. Set is linearly independent. So therefore, this C1, C2, Cn is linearly independent. So therefore, this will form a basis of Cn cross 1 column vectors. So then that is then any vector x can be written as linear combination of C1, C2, Cn. In fact, whenever you have a unitary, basically whenever you have a unitary matrix, so each columns will form an orthonormal basis, orthonormal set. They are orthogonal, and in fact, those columns will form a basis of the vectors, basis of the space, whatever the Cn cross one, and they will be orthonormal basis. There is those things will be. I will be discussing some of the problems from here in next tutorial. So for today, this is also the last option is. So, but last option asks that there exists some vector x which is not in the linear span of column A. So that means that as a statement this is not correct, because column space of A, that is a spanning set or basis of the Cn cross 1. So that means any vector x has to be there. So that's as a option, that's as a statement not correct, as a option is correct. So this is all. I will not go for 2 days. So if you have any doubt, you can ask. Otherwise, I will. Is this clear? Okay. So if you have any other doubt, you can ask. Otherwise, I will stop here for today. And the next tutorial will be as it is on the Saturday from 6 to 8 p.m. And I hope in the next from the next one I will not make any mess. Okay. Thank you. I will stop here.